All right, so chapter 6 is about a lot of the properties involved in intermolecular forces, but before we jump into that, really briefly, let's describe what's going on at a molecular level with solids, liquids, and gases. All right, sometimes it's a little bit hard to define what a solid is. Does anybody want to share just a generic term or descriptor? I always think of them as something that's rigid and has a fixed shape and volume. However, the individual molecules in there are actually vibrating. Does anybody know why? Think about the heat in the room, right? If you apply heat to these molecules, they actually will absorb that heat and vibrate a little bit. But not flow. All right, so when I used to teach in a K through 5 setting, I used to do a solid, liquid, and gas dance, where the solids, I would have them vibrate in their desk. The liquids, I'd have them get up and roam around the room, and then the gas, they'd jump around the room. You can always think of it that way too if you want to do a solid, liquid, gas dance. All right, a liquid, on the other hand, doesn't retain a fixed shape, but it will fill the bottom of a container. And they flow freely. Sometimes the difference between a solid and a liquid can be a bit more complicated than that. So if you think about something like a landslide, right? If the side of a hill actually slides down, is that a solid or a liquid? Well, it's kind of acting like both. There are some situations where you run into solids that behave a lot like liquids. Those are often called non-Newtonian fluids, so they don't really have the property of a true fluid or a liquid. There's some cool videos. Does anybody watch Mythbusters? I know it hasn't been on for a while. They had one where they actually filled a pool with cornstarch and water, and they were able to run across it, but if you stand, you'll sink into it. That's an example of a non-Newtonian fluid. All right, gas, on the other hand, fills the entire volume of a container. And they move really fast. So basically, gas molecules zip around a room, and if you spray perfume in one corner of a room, really quickly those molecules will find their way into the opposite corner of the room, which is why you can smell perfume when it's sprayed many meters away. All right, so I know a lot of this is general review, though. Yep?
To clarify, a gas will expand to fill its container, but a liquid won't?
Yes, exactly. So a gas will expand to fill its container very, very quickly. A liquid will just hang out on the bottom of the container, assuming that we're in a situation where we have gravity and we're not floating around in space. Yeah. All right, so a lot of this is review. However, it leads us to our next point about phase changes. And chemists have a lot of terms for various phase changes that occur when you're moving from one state of matter to another. Some of these are pretty intuitive. So the first one you're probably very familiar with is melting. So if you take an ice cube out of the freezer, put it on your countertop, it will melt. So you're going from solid water all the way to liquid water. And then the next one is similar. Vaporization. What happens with vaporization? What is vapor? It would be a gas, right? So it would be a liquid going to a gas. It's not a trick question, I promise. So if you, let's say, leave your water out on your counter for weeks and weeks and weeks, eventually that water will evaporate and turn into a gas. The next one is the opposite. This is condensation. That's where you go from a gas to a liquid. A good example of this would be walking through the grass in the morning. It's very dewy out. That's because a lot of the humid air has condensed on the cold grass. All right. Freezing is another one. Freezing is where you go from a liquid state to a solid state. So the easiest example of that is making ice cubes in your freezer. And then there's one last one that you might not be as familiar with. This is called sublimation. Does anybody know what sublimation is? What do you think?
It's when something is frozen and actually evaporates.
Yeah, it's when something frozen evaporates. So you go directly from a solid to a gas without going through the liquid phase at all. Does anybody know a good example of this? What do you think?
CO2 blocked with dry ice.
Yeah, exactly, dry ice. If you get it from the store, the reason they call it dry ice is it doesn't melt. It goes straight from solid CO2 to a gas. There's also the opposite called deposition, where you can go from a gas to a solid. But that's more a rare example. So sometimes you can actually plate out a gas into its solid phase. It's often done in the semiconductor industry to have a really thin coating applied to a material. All right, so oftentimes when you're looking at these diagrams, it'll show you a transition range. So for example, in this one, when a solid warms, that will take a certain amount of energy, and then you will undergo a melting process. So melting is one of the key terms we need to remember for this class. And then once that liquid's melted and warms, it can vaporize and become a gas. And then once you're in the gas phase, it can cool down and condense. And then once that liquid is cooled more, you can actually go back and freeze it. So those four terms are the main ones I want you to know from the class. Sublimation and deposition are kind of odd examples, and they depend a lot on pressure too. So does that make sense? I'm assuming most people know about solids, liquids, and gases at this point in their lives. All right, so let's move on to something more interesting. Intermolecular forces. So let's first talk about intermolecular forces. All right, and the key part of this is the prefix inter. If you think about interpersonal relationships, that means your relationship with others, right? So this is basically the interaction of molecules between one another. And these are referred to as non-covalent because a bond isn't being formed. Between two or more molecules, atoms, or ions. The key thing, though, is when they interact with one another, they're not forming any bond. They're basically just kind of sticking together for a brief moment. So in the example picture that I have shown here, we've got a bunch of water molecules, so it's H2, 2 hydrogens for every oxygen. So it's H2O, and these water molecules like to stick together a lot. So an example of an intermolecular force can be seen right here and right here. So it's basically these water molecules sticking together. So intermolecular forces describe the stickiness of molecules. So basically it describes how well one water molecule sticks to another. If we think about intramolecular forces, where we change the prefix from inter to intra, that describes something like a covalent bond. So it's a force within one molecule, not a force between two molecules. So it is important to distinguish those prefixes. Yep?
Does this have anything to do with the net dipole, the polar molecules?
Yes, absolutely. So we're going to go back and talk about net dipoles and how this relates to intermolecular forces. Yep. All right, so let's come up with a little chart here. Got intermolecular forces. And oftentimes I call these IMFs, not the International Monetary Fund, but the intermolecular forces of a molecule. And stronger intermolecular forces lead to a variety of things. The first thing is typically if you have a stronger intermolecular force, you have a higher boiling point, meaning it takes more energy or more heat to get something to boil. Second thing is you typically have a higher freezing point. Which makes sense, right? If we think about things sticking together, if they're really, really sticky and they grab onto one another, it's going to take more energy to rip them apart and get them to go into the gas phase, right? So it's a pretty general abstract idea here. All right, and I'll show you an example of this in action. Let's take water and compare that to methane, which is CH4. If we think about the molar mass of water, it's going to be the mass of 2 hydrogens and 1 oxygen. So it'd be 18.02 grams per mole. If we think about the molar mass for methane, it's going to be pretty similar. So we've got 1 carbon atom that's 12 AMU, 4 hydrogen atoms, so it'd be 16.04 grams per mole. So really the difference in their molar mass is less than 2 grams per mole difference, right? So it's a pretty minor difference in the grand scheme of things. All right, if we look at the properties of these 2 compounds, though, they behave radically differently. Does anybody remember what the boiling point of water is in Celsius? 100, that's an easy one to remember, assuming we're at standard pressure, so sea level. And methane, on the other hand, is found in natural gas, which gives you a clue that it's a gas. To get methane to boil and to become a gas, you just need to have it at negative 165 degrees Celsius. So it's actually really hard to get methane in anything but the gas phase because you have to cool it down so much. If you follow the local news, this has been talked about pretty heavily in the Tacoma area. Does anybody know why? The liquid natural gas plant in the tide flats. So they've been talking about that. Those plants, what they do is they basically take in natural gas, they pressurize it, they cool it down a lot so that they can actually take a gas that takes up an enormous amount of room, condense it down into a liquid phase. That's a lot smaller, easier to transport, easier to ship to a foreign country, or easier to ship via rail cars or shipping. So yeah, kind of bringing it back to the local idea. If we think about which of these has the stronger intermolecular force, which one do you think has a stronger intermolecular force, water or methane? It must be water, right? So we'd say higher boiling point equals stronger IMFs. Water is much more sticky. Than methane. Does that make sense? So next what we're going to do is we're going to try to name some of these interactions, and there's a whole bunch of them. We're just going to hit the main important ones. And the first one goes by a variety of different names. It's kind of like a tomato-tomato situation. This can be called dispersion. It can be called van der Waals forces. Oops, that should be a W, not a U. It can be called London dispersion. Or it can be called instantaneous dipole. It really depends what textbook you're looking at and what country you're in. Usually in American schools we refer to it as dispersion forces, but all of these apply to the same phenomenon. These are really common. In fact, they occur between every molecule of any type. And they are between two nonpolar molecules. And basically it's the result of electrons being thought of as particles, right? So let's kind of zoom into this. If you have two different molecules, they've got these big electron clouds. Electrons, because they're particles, will kind of scatter around into a statistical probability map around a given central atom or molecule. However, if you stop and you take a picture of that at one given point in time, you might have a picture where the molecule on the left has more electrons on the left-hand side than on the right-hand side. So we call that an instantaneous dipole. That's one snapshot in time. And this can happen between two molecules where you actually have matching ends, where one end of one molecule at one point in time is electron deficient and the other one is really electron rich. So it basically describes how nonpolar molecules stick together. It's due to the fact that electrons can't be everywhere as once. All right, so let's kind of describe this a bit more. It's due to a momentary imbalance of electron density. Typically, this interaction is thought of as weak. Because it happens so quickly and breaks apart so fast, the interaction is pretty short-lived. But I'm going to put weak into quotes here because this really, really depends. There are examples of dispersion forces that are incredibly strong, and I've got an example here of a gecko's foot. If you think about geckos, right, geckos can climb walls. The question is, well, what's actually causing them to stick to the wall? If you ever feel a gecko foot, it's not wet or slimy or sticky in the common sense. What happens is if you zoom in on a gecko's foot, you see all those pads. You can zoom in even further, and there's ridges within those pads, and then there's ridges within the ridges, and then there's ridges within the ridges of the ridges. So there's a huge amount of surface area on gecko feet. That basically allows them to have dispersion forces with the things that they contact, and then they can rip that off and go up one more step and keep on doing that. If their feet were too sticky, they actually couldn't rip them off the surface, so they found this perfect balance of surface area and intermolecular forces. So let's write that down. So geckos climb using dispersion forces. And I did want to make a really important note that surface area increases the stickiness of a molecule. In fact, if you buy some climbing gloves or athletic gloves, like for football, they figured that out. So they, especially with football gloves, they feel really rough because they have a huge amount of surface area, but that allows a football player to reach up and snag a football without cheating and applying some sort of sticky substance. It's just a surface area gain. Yep.
Would a gecko be able to then climb like a charged surface? Like if you were running a current through a surface? Would
that would be a different question. So the question was, what about climbing a charged surface? That would imply there's electricity going through there. That would be a pretty unhappy gecko. There would be some other problems going on there. So yeah, I don't really know what would happen then besides it shutting down that little gecko's heart, which wouldn't be fun. All right. So that's an important one, generally thought of as weak, but like I said, it depends on the surface area a lot. The next one we're going to look at is called dipole-dipole forces. And these are the next up, and this is the interaction between two molecules that are polar. Two or more molecules that have net dipoles. What do we need to know before we can determine whether or not a molecule has a net dipole? We actually saw this on the exam. Do we just need to know the formula? This is a tough crowd this morning. Everyone's tired. What else do we need to know besides the formula? You need to know electronegativity. All right, is that it? Yeah, so you need to know the differences in electronegativity, but there's one other huge feature we need to know. Think about your molecular modeling lab. Yeah?
You need to know the molecular geometry.
Yeah, we need to know the shape, right? Whether or not there's a difference in electron density depends on the overall shape, right? Sometimes that tug of war cancels out, other times it doesn't. That impacts the overall net dipole. So I'm going to put down here that you need to know the 3D shape. Knowing the molecular formula or whether or not there's an electronegative atom is simply not enough. You need to know the 3D shape before you can determine if a molecule has an overall net dipole. All right, so let's take a look at an example on the left here. The example on the left, I'm actually going to break this down the middle, is a solid. And solid molecules, molecules in the solid phase are pretty interesting. So maybe right here we've got a partial positive end on the right-hand side of a molecule. That'll pair up with the partial negative end of another one, and then so on. And then that can actually go three-dimensionally too, right? So not just across, up and down, but in and out of the page. So you end up oftentimes with almost a lattice network or a brick wall where you're trying to pair up opposite ends. So partial positive side will always pair up with partial negative. So let's take a look at that. These really like to pair up with one another. Opposite charges attract. If you think about a liquid, this can still occur. However, they flow around in space, so the positive will still pair up with the negative, but it's not as structured. You can't really think of it like a brick wall anymore. It's more like a flowing glob of stuff that's sticking to one another. Does that make sense? All right. There is another really special type of dipole-dipole forces that shows up a lot in biology, so I wanted to talk about that. You can actually see down below. It's called hydrogen bonding. And I'm going to put bonding in quotes because it's not a true ionic bond, it's not a covalent bond, it's actually its own unique type of interaction. Some people think of it as a bonding interaction, some people think of it more like a non-covalent interaction. The truth is somewhere in between. So let's make a note of what's going on with hydrogen bonding. It's a type of dipole-dipole that is very strong. A good way of thinking about hydrogen bonding is a hydrogen atom is shared. between a lone pair and an electronegative atom. All right, if we think about the most electronegative atom, what would that be? It would be fluorine, right? The closer we get to the top right-hand corner of the periodic table, the more electronegative we get, with the exception of the noble gases. So fluorine would be an example of a good partner for hydrogen bonding. The other one that's common is oxygen, and then the third one is nitrogen. So I call this the phone. If you have a hydrogen coming off the phone, it can often participate in hydrogen bonding. So let's take a look at some examples. If we think about hydrofluoric acid, this fluorine atom right here has a bunch of lone pairs. So we immediately have a lone pair coming off. And then we also have a hydrogen right here that is covalently bound to fluorine. The reason that this occurs is that this fluorine atom, let me actually rewrite this, is really electron rich because there's a net dipole, right? If we think about the net dipole is going to hog electron density away from the hydrogen, so that's electron rich. And then conversely, if we think about this other HF molecule, it's got a hydrogen that's incredibly electron poor. So it is still a type of dipole-dipole, but that hydrogen right here is essentially being shared between two fluorine atoms. So I almost describe it like a track race where you hand off a baton, but you don't let go, right? So a hydrogen bond, that hydrogen is essentially shared equally between both fluorine atoms in this specific situation. All right, we can also look at this with water too. So in water, the hydrogen atoms are essentially shared between two oxygen atoms. So like I said with that baton analogy, it's handing off one hydrogen to the other one, but essentially not letting go. That hydrogen is in many ways shared between two central oxygen atoms. So like I said, there's a really simple trick that I use. And that is to ask yourself, is hydrogen on the phone? Meaning fluorine, oxygen, or nitrogen. And then if your answer is if yes, there is H bonding. The most important thing, though, your hydrogen has to be directly attached to a fluorine, oxygen, or nitrogen. It can't be multiple atoms away. That won't do hydrogen bonding. Does that make sense? Yeah.
Would this kind of hydrogen bonding happen between, say, oxygen and the hydrofluoric acid?
Yes. So if we mixed a hydrofluoric acid and water, is that what you mean?
Yeah.
Yes, then you could still have hydrogen bonding between two unlike molecules. The key thing is one molecule needs to have a hydrogen on the phone, and the other one has to have a lone pair available. In that situation, though, the hydrogen might not be shared evenly between two atoms. Does that make sense?
Yeah.
All right, so hydrogen bonding is a really, really important thing in biology. How many of you are planning on taking biology at some point? A few people? That's good. Biology is really fun. So let's talk about some of these special features and how they relate to biology. Does anybody know what this compound is on the left? Looks like DNA, right? So on the left, we've got a double helix of DNA. And H bonding is what actually holds the two strands of DNA together. It's really important, right? And then we have these enzymes that will read your DNA, basically rip apart that hydrogen bonding like Velcro, read it, go down the entire strand, and then it will stick back together again, and that's how we replicate our DNA. So we want to have this reversible stickiness between our two strands. We want it to stay together to protect it, but we also want it not to be too strong so we can rip it apart and read it as needed. If you're familiar with biology, we have two different base pairs in the middle that actually link these strands together. So on the left, what we have is the symbol G, that's for guanine, and on the right we have C for cytosine. And in this specific interaction, we actually have 3 hydrogen bonds. So first thing I would do is look for a hydrogen on the phone. So I see one right there, nitrogen with a hydrogen. See one right here, nitrogen with a hydrogen. Then one here, nitrogen with a hydrogen. So those are capable of hydrogen bonding, but they need a lone pair to hydrogen bond with. But that's okay because this oxygen right here has 2 lone pairs that can actually share its electron density with that hydrogen. And then down here we've got a nitrogen with the lone pair. Just like the other one, it can share electron density. And then up here we've got 2 lone pairs that can share an electron density here. So this specific set of base pairs will actually stick together through 3 separate hydrogen bonds all at the same time. Yeah?
So in biology, when referring to DNA, only G and C can bond?
Yes, only G and C can pair through hydrogen bonding.
And the same is true for the A and T?
Yes, the same is true with A and T. We're actually not going to cover that too much. I'm going to leave that for your biology instructors. I don't want to give away all the fun of biology. But I did want to explain that these interactions are really important for understanding the function of DNA and the structure of DNA. One quote I really remember from when I was in school was I had a teacher tell me that biology is really chemistry, chemistry is really physics, and physics is really math. All of the STEM fields kind of blur together. All right, so that's one really important feature. Another one's also related to biology. H bonding holds proteins together. Specifically, it helps them to fold into correct shapes and structures. In particular, there's 2 classic shapes. The first one is called an alpha helix. It's basically like a big spiral. So oftentimes, if you look at the overall structure of a protein, it has these basically curly fry sequences to them, where you've got a bunch of amino acids that are bonded together, but they kind of spin around in sequence. So they have these spiral shapes. Another one is a little bit different, where you have a beta sheet. And essentially, these are where you have 2 different amino acid chains basically touching side on, and that will give the overall protein a lot of structural shape. Proteins are enormously big. So most of the molecules we've been looking at contain just a handful of atoms. Proteins contain oftentimes tens or hundreds of thousands of atoms. So they're amazingly complicated. Yep.
So when you feed up a protein, it denatures and unfolds.
Yeah.
Is that because the hydrogen bonds?
Yes, that's a big part of it. So when you denature a protein, you're often ripping apart the hydrogen bonding that changes the overall structure of the protein. So my favorite example of that is an egg, right? If you crack an egg into a frying pan, you're applying a lot of heat that can rip apart hydrogen bonds. You actually get some chemical reactions taking place too by ripping apart those hydrogen bonds. And is that a chemical or physical change? Be chemical, right? You can't unfry an egg, at least not that I know of. So you're doing an irreversible process by essentially changing the structure of those proteins in eggs and allowing reactions to occur. Yeah. All right, the key thing to remember with this is if you have a protein that isn't folded in the right way, meaning the hydrogen bonds aren't linking up the right way, that can lead to a whole variety of problems. So misfolded proteins leads to disease. So if you think about how proteins are made, some of you might remember this from high school. Proteins are coded in DNA. So DNA basically contains the blueprints for proteins. If one of those base pairs in DNA is off, your protein won't be made the correct way. It won't fold the right way. You might have a completely different shape of your protein. That means that you might have some awful disease. In fact, my family has a lot of genetic diseases in them where proteins aren't made or folded correctly. So some of my family members actually have diseases related to this. It's really interesting, so if you are interested in medicine, you're probably going to learn about this a lot more. All right, the other interesting thing is how this relates to water. So H bonding results in water being less dense in its solid state. As a solid compared to a liquid. So most compounds, when you cool them down and you freeze them and they actually get more and more dense, those molecules will pack more tightly, and so they have more mass per volume. Water is actually the opposite. When you cool water down, water stops flowing as freely, and it will actually stack with other water molecules in a very specific fashion, but that actually increases the volume of the overall system, making it less dense than its liquid phase. This is hugely important from an environmental standpoint. Like I said, most liquids, when you freeze them, will sink. Ice cubes will float. If you think about our polar ice caps, that's very important, right? That ice floating goes to the surface of the Arctic, and then that ice will actually reflect sunlight back into space and keep our planet somewhat cool. If that ice were to sink, our planet would be incredibly hot, so hot that we couldn't support life. We'd be a gas planet instead. So that's an important feature related to Earth science. The other one I've got here is something you actually saw in class. What do we call this U-shape? A meniscus. So you saw that in lab when you were measuring things in a graduated cylinder or in a burette, and that's actually due to hydrogen bonding. If you think about water, water very much wants to stick to other things that can hydrogen bond. Glass can actually participate in hydrogen bonding, which basically pulls it up against the glass. The glass wants to stick to that water, it doesn't want to let go, and it can actually pull it up a fair amount. So let's make a note here. So SiO2 is the molecule that's in glass, silicon dioxide. Sticks to water. And pulls it up. If you think about an element like mercury, that's a metal. It has a very, very different intermolecular force. In this case, you actually get the opposite effect. You get an upside down meniscus because the glass very much does not want to stick to mercury. So you actually get this kind of bubble sticking up. But that's all due to intermolecular forces. All right, the last one is actually related to what I worked on. This won't be on the exam. So when I was in graduate school, I actually made and designed molecules that were specific hydrogen bond acceptors and donors. And in particular, what I did was I made this big molecule over here on the left. And if we look at it, we want to identify hydrogen bonding features. So for example, I've got a hydrogen on the phone there, hydrogen on the phone there, hydrogen on the phone here, hydrogen on the phone here, and they're all pointed into one interior pocket. And I've also basically handcuffed it together on the bottom so that it can't flail around too much. That means that if I have something with a lone pair, it will just snuggle inside of that pocket and be held onto by a bunch of hydrogen bonds. So what happens is if you throw in something like chlorine, it can hydrogen bond through this top position right here, 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 and here. So we can trap certain molecules through hydrogen bonding. The cool thing with this was it actually changed the color of the overall molecule too. So basically when it had nothing inside of its pocket, it was a different color than when it found something to hug and hold on to. So we actually turned this into a system of molecular sensors that would change color when they found a specific molecule. There's a huge number of applications for this. One of my favorite ones is in the airport. Have you ever been swabbed when you go through the airport? It's becoming more and more common. Oftentimes what they're doing is swabbing your hands. If you have explosive residue on your hands, they'll actually pass it through a system of molecular sensors. If it lights up and says this person has been in contact with explosives, they will screen you further to make sure that you're not carrying a bomb or a gun or anything like that. We actually use this to detect a whole variety of different anions. The coolest one, in my opinion, was we found one of these types of molecules that would wrap onto fertilizer molecules and change colors. And so we developed it into a product that would tell farmers if they over-applied fertilizer into their fields. That way, if they over-applied, they'd know, hey, we need to back off, or if they didn't have enough, they'd say, hey, we need to add more. If you add too much fertilizer to a field, what happens? Does anybody know? It can kill the field, and it gets run off in the local waterways, which poisons things like Puget Sound, leads to big oxygen depletion areas. So I think it's pretty interesting. Tomorrow, when we come back in, we're going to talk more about the relative strengths of these and probably even move on to a new chapter.